All right, so yeah, like I just mentioned, welcome back, and let's quickly look at this example. This is a challenging question, not something I think you would see on your final or on a test or anything, but it's a good kind of practice problem for thermochemistry. So the answer is here. Oh, okay, good. Whew, I was nervous my pen wasn't going to work again, but it's working. Okay, so the answer is here. It's about 140 degrees Celsius with the significant figures. So how is it done? Well, the first thing you need to think about with this example is what is the system and what is the surroundings? So the system here is the copper. That's what we're studying. We're trying to figure out the initial temperature of the copper. The surroundings would be the water and the beaker and the air around it. But of course, we ignore all that. We only consider the surroundings, the water. So 50 grams of copper is dropped into 125 grams of water at 20 degrees Celsius. The final temperature of this, system and surroundings, like the final temperature of, I don't want to say mixture, but the final temperature of the copper and the water was 24.2. So the question is, what was the initial temperature of the copper? This is, again, a very like a challenging question. So this is just kind of meant for practice. So the first thing you do is you will find the heat, and let me change my color here. I'm going to go with orange. You want to find the heat of the water. Okay, the Q of the water. We don't have enough information to find the heat of the copper, but we do know that we have the mass of the water. We know we have the heat capacity of the water, and we know we have the delta T, the change in temperature of the water. Now, the water, very important, is the surroundings. Okay, so Q is MC delta T. Now remember, because this is not a homogeneous solution, this is not a mixture, we do not need to add the masses together. The water is separate from the copper. They do not mix. So M, 125 grams of water. C is a constant. Again, I typically have students ask me where that number comes from. Where does the 4.184 come from? That is a constant. It's the heat capacity of water, a specific heat capacity. So, just like gravity or pi, this is a constant from your data booklet. And of course, I have delta T. So I multiply all that together and I find out that the water absorbs 2,196 joules, so around 2,200 joules of energy. Remember, this is the surroundings. This is what the water is absorbing. Harold, yeah, so we only round at the end, at the last part. I'll talk about the test a little later today. Who asked that question? Sorry. Nara's, I'll talk a little bit about that after today's class. But yeah, so Harold, we only round at the end. And again, I'm not too concerned about significant figures or rounding, but in your labs, you want to be really careful with that. Okay, so the water gained 2,196 joules. So that must mean that the system, this would be my copper, lost the same amount of energy. Okay, and now that I have all that information, I can plug it into Q is MC delta T. Now, this is where the question gets difficult. And this is like the chemistry is over here. There's no chemistry after this. This is a straight up math question where you guys have to solve for the initial temperature. Okay. I'll kind of leave that for you. This is, again, this is just math. It's not chemistry. You know, you guys can practice to solve this on your own, but we're going to solve for T1 in this equation. Again, it's asking for the initial temperature of the copper. So just to kind of, give you a little hint, I guess, about this, this should be negative, as Iman told me yesterday or mentioned to me yesterday. That's a little typo there. So this should be negative because it's negative up here. So this is my Q. My mass of copper is 50. The heat capacity of copper is 0.386. That's in the question. And the final temperature, or I guess we would call it T2, is 24 degrees. So you guys would have to solve for T1. Again, I'm not going to go over the math in chemistry class, but if you guys, anybody here needs help with algebra or math or rearranging equations, you can check me out in my office hours. They're posted on D2L. So if you guys have any questions or need help with the math, you guys can let me know. They're not both negative, Aman. The surroundings is positive. You can see it here. I guess I'll pick another color. I'll go green. The surroundings are positive and the system is negative. Okay, they cannot have the same sign. That like would violate literally the laws of the universe. The system and surroundings cannot both be negative. They cannot both be positive. They're always opposite in sign. So the surroundings, as you can see here, I'm underlining it in green, is a positive number. The system is a negative number. They cannot be the same. It is literally impossible. All right, cool. So I hope you guys had a chance to practice that. It is a good question. But again, a little bit challenging, I guess, for say like a final exam or something. So let's get into the next section. Let me share my screen again. In this section, hopefully I can finish this today. It's on enthalpy. And we talked a little bit about this yesterday. Well, no, actually, I guess we didn't. We kind of ran out of time. But enthalpy is probably a new term for a lot of you. I mean, you've obviously heard about mass before, temperature before, and you've heard of the idea of heat. But you probably have never heard the word enthalpy, maybe in your high school chemistry. It's not a very hard concept in 1121. We keep it pretty simple. So these are some of the objectives we're going to look at. And let's get started with what is enthalpy. So enthalpy is the total kinetic and potential energy of a chemical. It's directly related to energy. You can almost think of enthalpy as another word for energy, and it's directly related to the heat energy of a chemical. The symbol for enthalpy is, of course, it can't be easy. It's an H. So the symbol for enthalpy is H. You'll see it a lot in chemistry written as delta H, or the change in energy of a system. So a really easy way to think about this is if you see the word enthalpy in chemistry, just think of energy, okay? And it is related to thermochemistry, meaning it's directly related to heat. So the units for enthalpy are kilojoules per mole or joules per mole. So you can kind of see where this number comes from. Your enthalpy is the heat, which is joules or kilojoules, divided by the moles. Do you guys remember moles from chemistry 1120? It's back. So in chapters 2 and 3, we will be talking about our good friend, the mole. And we'll talk about this formula today as well. Now, this formula on the bottom, sorry, I didn't even know that was going to show up. This formula on the bottom, you will not need in for a test or anything like that, but it is a way to calculate the change in energy, delta H. It's the products minus the reactants. It's not really needed in this chapter. We're going to do something a little bit different to calculate delta H. So if delta H reaction, is positive, and this is something I mentioned the other day, a really good way to tell if a reaction is endothermic or exothermic is to look at the sign of delta H. The sign meaning, is it positive or negative? So if delta H is a positive number, so say I do this subtraction here and I get a positive number, that must mean the energy of the products is the bigger number. So that means the energy of the system has increased, and this would be endothermic. So what you need to know from this slide is that if delta H is positive, the reaction is endothermic. The fact that delta H is positive means it's gained energy. The change in energy is increasing. And when a system's energy increases, it absorbs energy. So the big thing here, I had a student last week tell me, what do we need to know? Endothermic reactions are positive. Endothermic are positive. So, of course, if the reaction is negative, so if delta H is negative, it's exothermic. This means that the system has lost energy. When a system loses energy, it gives the energy away, which is the exact definition of exothermic. Remember, you can think of exo like the word exit. The energy exits or leaves the system. So when delta H is negative, when enthalpy is negative, it's exothermic. So again, make sure you know that. All right, let me just check the chat here. Yeah, so as Abdul Halim says, we are studying the change in energy, not the energy itself. Yeah, exactly. We're looking at the difference in a chemical reaction of the energy of the products and the energy of the reactants. So what that means is when a chemical reaction happens, we're looking at the energy. Did the products gain energy or did they lose energy? Is it absorbing energy or releasing energy? And when I say energy in this context, I mean heat. Is the reaction losing heat or absorbing heat? But again, all you need to know is that when delta H, when enthalpy is negative, negative, it's exothermic. When delta H is positive, it's endothermic. So make sure you know that. You might want to write that down or keep it in your mind. You will see this again. So the change in energy of a system can happen in two different ways. I'm teaching this term Chemistry 1120 Labs, and I don't know if you guys remember the lab in 1120 where you melted and you froze lauric acid. It was like that white waxy substance where you put a thermometer in and you melted it and then you kind of re-solidified it or froze it, I guess is what we would call it. That was a change in energy. That's a physical or phase change. So the energy of a system can change by phase changes. It can melt, it can evaporate, it can freeze. Any phase changes will result in enthalpy changes. Another way that the energy can change in a system is by a chemical reaction. So double replacement, neutralization is a good one. You guys did neutralization in your your second lab. So neutralization is typically exothermic. When you mix an acid and a base, it typically gets hot. It releases energy. Combustion, so burning a candle or burning a piece of paper, also going to result in energy changes. So enthalpy, you can see an energy change in two ways. It can be a physical change, like a phase change, or a chemical change, like a chemical reaction. So is melting endothermic and exothermic? Is freezing endothermic or exothermic? This is a really good kind of thinking question. When you think about these things, you need to think about the chemical, like you could think about an ice cube as the system. When you melt something, does it release energy? Like, does it release heat or does it absorb heat? What do you guys think? When you melt something, does it release heat or absorb heat?
Absorb.
Yeah, exactly, absorb. When you release, sorry, when you melt something, you're putting heat into the system. So as someone just said in the chat, and on the speaker, and Manal and Noor, it's absorbing heat. To melt ice, it needs to absorb heat. So this would be endothermic, which means delta H is positive. We're putting energy into that system. Now, the easy thing about this is freezing is the opposite of melting. So freezing, and I know this kind of sounds weird, but freezing would be the opposite of melting. So freezing would be exothermic. Heat is getting released, it's getting colder. So the way a freezer works or a refrigerator works is they pull heat out of your food. So if you put something in your refrigerator, why does it get cold? Well, the heat in your food is released. It leaves the food item. So it would be exothermic. And I know that sounds weird because you guys are probably thinking, hold up, a combustion reaction, an explosion. How is that exothermic, and freezing is also exothermic? But they're both releasing heat outside of themselves. So you put a hot piece of chicken in your refrigerator, all of that heat gets released into the refrigerator. You light a candle, all of the heat in the candle wax is released outside of the candle. Little weird to think about. There was a question in the chat there from Aman about what you need to know, or do you need to know? I think she was talking about this slide. Yeah, I mean, it would be good to know that enthalpy can change in two ways. It can be a phase change or a chemical reaction. That would be good to know. All right. Cool. Oh, and a little note on the bottom of this slide, melting and freezing, I have it is the same phase change, just in reverse. So melting is solid to liquid, freezing is liquid to solid. So they actually have the same energy change for them, just different signs. So this slide, okay, so sorry, I got a question in the chat. Melting, okay, think about when you're melting something. When you're melting a, like say an ice cube, the ice cube is getting warmer. You are putting energy into the system. It's not releasing energy. When something releases energy, it gets colder. This is absorbing the energy. So like as Harold says, it's getting heat to melt. So because the system is absorbing heat, it's endothermic. I hope that makes sense. It can sound a little confusing. Now, this slide, you don't have to know too much about it, but one thing is important here, and I'll kind of comment this on the bottom. The enthalpy changes for chemical reactions are typically much, much larger than physical changes. So the energy involved in melting water is a lot less than the energy involved in actually chemically making water. So the only thing you really need to know here is this on the bottom. The energy, the enthalpy involved in a chemical reaction is a lot bigger than the energy involved in a physical or phase change type of reaction. So again, to freeze water, it releases 6 kilojoules. To chemically form water, it would release 286 kilojoules. Again, all you really need to know is that the energy involved in a chemical reaction is bigger. I don't know how good you guys are at math. This means greater than the energy involved in a physical change. All right, so now we're getting to where I wanted to be today. You guys will have to know this for a test or final exam. These are really easy to draw, so I'm going to kind of show you how to do this. We're going to get more into this in Unit 3, which we won't start for another week or two, but we'll look more in detail about this in Unit 3. But hold on now, I just want to see, sorry. Sorry, I'm just checking something out. Okay. I just want to see what was coming up. Oops. So yeah, we'll talk a little bit more about this in Unit 3, but we're going to draw kind of simplified ones in Chapter 2. A enthalpy or energy diagram shows the energy of a reaction as a graph. It really lets us see if heat is released or if heat is absorbed. The energy is on this axis, on the y-axis. Okay, and then time, or the process of reaction, you could call this time, is on the bottom. And we're going to kind of practice this today. This is basically all I wanted to show you today. So this is the enthalpy diagram for water formation, the formation of water. Here on the, and it's always like this, on the left, you always have reactants, and on the right, you always have products. Now, the energy, the enthalpy of a reaction is always the difference between the energy of the products minus the energy of the reactants. Now, how could we figure that out without, using crazy formulas? Well, it's pretty easy. We can use the graph. So the difference between the reactants and the products is here. This shows me that the reactants have 500 kilojoules and the products have 200 kilojoules. So the reaction here would be exothermic, and the difference here is negative 300 kilojoules. Okay, so I took the 200, subtracted the 500, and I get my negative 300. So this is obviously an exothermic reaction. And you can always tell if a reaction is endothermic or exothermic by looking at the shape, of the graph. If the products have lower energy, it means it must be releasing energy. It's exothermic. If the products have higher energy, it must be absorbing energy. So it's endothermic. This you should definitely know. And it looks a lot harder than it is. It's actually quite simple, and we're going to practice some of this today. Don't worry. And yeah, as Abdul Halim, and well, sorry, Aman, yes, you will draw this. And as Abdul Halim asks, can we immediately tell if it's negative or positive from the graph? Absolutely. If the products are lower, it's negative. If the products are higher, it's positive. And again, think about that, guys. If the products have less energy, the chemical reaction must have given away energy. If the products are lower, it's losing energy. If the products are higher, it must be gaining energy. So exothermic versus endothermic. Some of you guys might be wondering what is up with this. Why is there a lump in the middle? We're going to talk more about that in Unit 3, but I will give you a little answer to that. Why is there that lump or hill in the middle? It's called the activation energy. Okay, so we'll talk a little bit more about this in Unit 3. But just to kind of give you a heads up or give you some information, that lump is the energy it takes to make the reaction actually happen. Most chemicals are stable. they don't necessarily react. They need a little bit of help. And there's like a kind of a funny image here, right? If you're sitting down watching TV, but you want to go to bed, you can't just magically appear in your bed. You actually have to stand up, walk to your bedroom, and get into bed. So a chemical reaction is the same. Most of them aren't just going to magically happen. They need energy to actually start changing. Okay. And even though they need energy to start changing, sorry, so I'm going back to this slide. Even though they need energy to start changing, so that you'll notice that they both have that like hump or lump in the middle, it doesn't mean they're all endothermic. Endothermic means that the products have more energy at the end. Exothermic means the products have less energy. So even though there's a lump in all of these, you can't say they're endothermic. Yes, they all need energy to get started, but the terms exothermic and endothermic refer, or they're referring to the final product. It doesn't matter what happens in the middle. Perfect. I'm glad it makes sense there. So let's practice. Let's look at this. I got 1, 2, 3 problems, and then that'll be it for today. We'll just do these 3 problems, and then that's it. Okay, sorry. So how about this? Let me do one to get us started, and then maybe I'll give you guys a couple minutes to try the other ones. So this question says, what is delta H? What is my energy of this reaction? And is it endo or exothermic? So there's a few messages in the chat there. I would imagine some of you already know that this is endo. Now, how did I know that? Well, my reactants are always on the left. My products are always on the right. Okay. My products are gaining energy. Now, how do I know that? Well, draw my line. The difference between the products and reactants is bigger. It's positive. The products are gaining energy. Here, and I'll write that down. I'll put it down up here. So products are gaining energy. So that means that this is endo. Now, the next part of this question is saying, what is delta H? So now we're going to have to make kind of like an assumption here. So I'll call this 48 kilojoules per mole. And this is obviously 20 kilojoules per mole. If some of you guys are doing this problem and you said it was 49, or if you said it was 47, that's fine. Actually, it might even be 47, but we're just kind of taking an estimate from the graph. So my energy is my products, 48, minus my reactants, 20. The answer would be 28 kilojoules per mole. That's positive. And I think it was Aman the other day asked, do we need to put positive in? Not really. You do need to put negative in if it's a negative number. But yeah, positive 28, which really answers the fact that this is endothermic. It's absorbing 28 kilojoules of energy. This hump in the middle is irrelevant. Like, it doesn't mean anything yet. We'll talk more about that in Unit 3. You do need to put it in there, but we'll talk about what that number means, or what the hump means in Unit 3. But you do need to put that little hump in there, and it doesn't matter how high you go. We'll talk more about this in Unit 3. All right. Somebody, Iman said the previous slide. Oh, now let me go back. Yeah, it's negative, Iman. It's negative. The question was on this slide, since it was XO, why wasn't it negative? It's clearly negative. Yep, no problem. All right, so let me see. What time is 4:05? Well, yeah, why don't you guys, well, okay. I think you guys can do this. If you're there, like, or if you have a piece of paper next to you, draw an enthalpy diagram for this reaction. Now, guys, it doesn't need to be perfect. I don't need you to do a scale like this. When I say draw an enthalpy diagram, I mean like you could just do it like this. I don't need a scale or anything like that. Like it's not a perfect graph. It's more of a sketch. So I'll put myself on mute, and you can try this one. If you have your notes open, you can also try this one. But again, it's only meant to be a very rough sketch. So I'll put myself on mute and I'll be back in 3 minutes. See how you guys did. All right, so again, like I literally just said, this is only a sketch. You basically have two options. Your graph could look like this, or your graph could look like this, right? We have endo and we have exo. It's clearly endothermic. Oh, I shouldn't say clearly. It is endothermic because the delta H is positive. So all you literally have to do to sketch this is, I mean, you can make the graph like this if you want to. It really doesn't matter. I'm just going to say, okay, well, we have our products here. We have our reactants here. And the delta H is 142 kilojoules per mole. That's it. That's all you have to do. Oh, and it might help to put the positive in. You definitely do not need the positive, but I find for enthalpy or thermochemistry, I do like to put it in there, but you don't need it. Now, some of you might have drawn this and you might have put energy here, blah, blah, blah. You don't need to. But if you did, that's perfectly fine. Again, for anybody wondering what is happening with this hump, we'll talk more about that in Unit 3. It is called the activation energy, which means it's the energy it takes to get that reaction going. All right, this one, guys, I'm just going to put the answer up here because it's getting late. It's already about 4:15. So this is exothermic, which means my graph will look like this. The energy has to be negative. Sorry, I didn't make my graph very big. And then I'm going to put my reactants here. So CH4 plus 2O2 and CO2 plus 2H2O. Guys, you might recognize this reaction from Chemistry 1120. This is the combustion of methane. And that's all you need to do. That's it. Okay. Cool. And you will see this. You will definitely have to sketch this on a test. All right, so that's it for me today. Now,